What's up, folks? Coach Bach here. Got some more follow-up on the force velocity curve. So when I first talked about this, I kind of glossed over the explanation for the trend and the shape of this curve. And I did that just because I didn't want the video to get too complicated. And also because I think the explanations are still somewhat speculative. You know, the research on this is not easy to do. This is not an easy thing to figure out. And I didn't want to get just too bogged down in that video. But I mentioned that it has to do with cross-bridge factors. Okay, so myosin-actin cross-bridge factors, things like attachment rate, detachment rate, and force per cross-bridge. Now you may have noticed I did not bring up titin protein when talking about the force velocity curve. I talked about it a lot in the length-tension relationship, but I left it out of the force velocity video because I didn't really see it discussed in the force velocity literature, and I didn't want to just share my own hypothesis. That being said, the role of titin was discovered because of its influence on eccentric muscle action, or on isometrics following a forced eccentric. Okay, so that would be the left side of the force velocity curve. In that research that elucidated titin, they activated the muscle, then forced it to lengthen. And that's the same thing that they do when testing the left side or the eccentric side of the force velocity curve. So one would expect some influence from titin to show up here as well. Now, what might that influence be? They talk about titin being a spring. The force in a simple spring follows the formula F equals Kx, where K is the spring constant and X is length or displacement. Okay, so that graph is simple. It's a straight diagonal line where the slope is K, the spring constant. Now notice, F equals Kx does not have velocity in it. Velocity is a non-factor. So the force velocity curve of a simple spring would actually be a straight line. The velocity doesn't have an influence. So if titin was a simple spring and it only engages when the muscle is activated and then forced to lengthen, then that would only show up during lengthening action. And so then that line would only show up on the left side of the force velocity curve. There would be an increase in force specifically on the left side. So just hypothetically speaking, let's say the force velocity curve just from cross bridges in the muscle looked something like this. Well, then you add titin, and let's just say titin were to be a simple spring, it would really just elevate this left side of the curve. However, as you got to expect, titin is not just a simple spring. Titin is a complex protein molecule. All right, this is unimportant, but just as a side note to appreciate the biological complexity, titin has 244 protein folding domains, has over 34,000 amino acids in one titin molecule. But the key point to understand is that titin is viscoelastic. That means it has viscous properties and elastic properties. Now, as part of that, the faster that you try to stretch it, or the faster you pull it apart, the more it resists, or the more tension is generated in the titin molecules. And that should sound familiar. That's the same trend that we see on the lengthening side or the eccentric side of the force velocity curve of muscle. All right, faster lengthening, higher force. Now remember, this data, the force velocity curve, comes from an activated muscle, all right? Which means that myosin-actin cross bridges are present and those factors are at play as well. But turns out, even if you don't activate a muscle, even in a passive context, this type of trend in the lengthening velocity and the force shows up anyway. So if you take muscle, let it stay relaxed, lengthen it to the point where passive tension shows up, then from there, stretch it further, and then do that further stretch at the same range, but at different velocities, you get different forces or different amount of resistance at those different stretch velocities. Here's an example of a study on this. They dissected mice muscles, bathed them in a relaxing solution, and then did this stretching protocol at different velocities. And this is the graph of length versus stress, or stress is basically force in this case. And so you can see that as you stretch further, you get greater force, but if you stretch at higher velocities over that same range, you get higher force. This is what the graph looks like when you plot the velocity and the force. You can see this is basically a mirror image of the lengthening side or the eccentric side of the force velocity curve. Okay, so faster lengthening produces higher force even in a completely relaxed muscle. So when we look at the eccentric side of the force velocity curve, passive forces from titin are definitely a big contributor to this. And this lines up with other force velocity data where they've tested this relationship at different muscle lengths, and at longer muscle lengths where passive tension is going to play a larger role, the trend in the eccentric side tends to be even steeper, or the forces at fast eccentric velocities are more magnified at longer muscle lengths. All right, so it all lines up with titin being a big contributor. Now, this does not mean that cross-bridge factors are not still at play, but titin is definitely a dominant factor here. So again, getting hypothetical, if we just had cross-bridge factors at play, it may be that eccentric velocity doesn't have much of an influence on those. And so this curve would basically just level out on this side. That might be the case. And then it might be the case that really the increased eccentric forces really all come from titin. So this entire upward trend that we see on this side might be from titin. All right, with all that in mind, let's talk about ballistic movements. Ballistics, basically a description of when you have a fast lengthening followed by a fast shortening, right? So it's the type of scenario that you get in your sprinting, your approach jumps, your plyometrics, okay? These key explosive activities that we're trying to train for. As I've talked about before, these types of movements involve very high ground forces. They also involve moments of very high peak forces in muscles or in tendons, okay? So tendons like the Achilles or the patellar tendon or like the hamstring muscles during sprinting have these moments of shockingly high peak forces. And some people have looked at that type of data and said that, you know, the force velocity curve does not really apply to ballistic movements. In fact, this view even shows up in super training, the legendary, you know, Bible essentially of sports training, right? And I just want to push back against that, like I did before when we talked about full body movements and the force velocity curve. Same thing here. It's not that the force velocity curve does not apply, okay? The force velocity curve is a property of muscle, and it's true regardless of what you're doing. It's just that these movements are highly complex and dynamic, and so, you know, one graph like the force velocity curve does not fully capture everything that's happening. So key thing to understand is that this curve comes from multiple tests done at constant velocity. Okay, so you have a data point here, a data point here, a data point here, a data point here. Each one of those is a test of muscle force during a constant velocity lengthening or shortening, right? All these data points are individual tests done at constant velocity. It's not as if this is one contraction that they measured during a vertical jump or something, right? And so you have all these constant velocity tests, and that's where we get this curve. Well, newsflash, ballistic movements or pretty much any movement doesn't have constant velocity. Instead, there's a whole bunch of changing velocity. There's a bunch of acceleration going on, right? And so, yeah, this is not gonna capture all that. So what we have in ballistic movements is muscles that are being suddenly loaded and suddenly activated at a very high rate. Now, prior to that, they may be lengthening or they may not, depends on what muscle and what movement exactly we're talking about. So maybe they're starting out on the eccentric side, or maybe they're starting out closer to isometric. Regardless, whenever you make contact with the ground, or whenever you explosively activate the muscle, you're going to get this fast acceleration towards shortening. So there's going to be this stiffening of the muscle that happens very quickly in these moments. And so you're going to be getting like drastic acceleration down this curve. So in that moment of stiffening, you have cross-bridge factors coming into play, right? Because of the muscle activation. You have titin engaging and resisting lengthening of the fiber. You have probably the connective tissue surrounding the muscle, right? So the epimysium, paramysium, endomysium. So your muscle fibers, your fascicles, and the whole muscle all have connective tissue sheaths surrounding it. And depending at what muscle length you're at, that's probably stiffening and resisting lengthening as well, because that fascia, that connective tissue, is also viscoelastic, right? And so all these factors are coming into play, and you get this fast loading of the muscle. So imagine, maybe it's lengthening fast and then it's stiffening, so it's like that, okay? So there's a lot of force, a high force peak that happens in that moment. Even if it's not lengthening really fast, if it's starting, more isometric, you still have this fast tensioning that's happening in that moment. Okay, and so you get these really high peak forces in the soft tissue, a combination of, again, contractile and non-contractile elements, and all of that equates to big muscle tendon unit forces, big forces into the ground, and it's all followed by like an explosive shortening and explosive release of energy that produces, big jumps, sprints, etc. That was a very rough description, but hopefully you get the idea. Okay, human movement is complex. The force velocity curve is a property of muscle, so it's always relevant, it always applies, but no, it does not capture everything that's happening when a person is sprinting, jumping, etc. All right, hope you found that helpful.